So this is notes 8, page 3, simplifying with radicals. On this page, we are assuming all variables are positive. So this looks like a monster, but don't make it too hard. Let's say I had just something like this. If you were going to do a problem like this, wouldn't you look at the coefficients and say, oh, I can reduce those separately, so that would be 5. And then you'd say, well, I got some common variables, I can reduce those, and so this is just 5x. So the radical part here is kind of like the variables, and this is the coefficient of the variables. So the first thing you really want to do is realize I need to kind of think of these as two separate reducing problems. So I'm going to think I'm going to reduce the coefficients of the radicals, and then I'm going to reduce the radical. Now, coefficient's really easy. 2 goes into 10 5 times, so that's 5p over 1. Then here, you don't want to start simplifying this radical and simplifying that radical. Simplifying radicals is a pain. Would you rather simplify one radical or two? I'd rather simplify one radical. So I know I have my rules for radicals. When you're dividing radicals, you can change this into one big happy radical. So that's what I'm going to do. Put this all under one big happy radical, and then reduce inside first. Okay. That doesn't look that hard, reducing inside, because remember the radical is an understood parentheses bar. I am just out of it. The bar is like understood parentheses. So this is 5p times the 5th root of, well, 2 into 64, that's 32. 4 p's cancel with 4 of those, p to the 8th. All right, that doesn't look that bad. Now I need to try to actually simplify the radical. First thing I did was simplify inside the radical. Then I want to see if I can pull anything outside this radical. Well, is 32 a perfect fifth? Oh, yes, it is. That's the one perfect fifth you should know. The 5th root of 32 is 2. Is p to the 8th the perfect fifth? Well, is 8 divisible by 5? No, it's not. So can I simplify it? Well, yes, as long as the exponent's bigger than the index, I can peel out some p to the fifths. So I'm going to write this as 5p times the 5th root of 32 times, all right, I need a p to the 5th to be a perfect fifth. So I'm going to break up p to the 8th as p to the 5th times p to the 3rd, because when you're multiplying the same base, add the exponents. I haven't changed the problem. And then I'm not going to write every step in great detail. I'm going to just think, all right, these are my perfect fifths. These I take the 5th root of. Now the 5p is still hanging out there, times, what's the 5th root of 32? 2. What's the 5th root of p to the 5th? P. And the p to the 3rd does not come out, it stays under the radical. And then finally, one last step, multiply the coefficients together. 5 times 2 is 10. P times p is p squared. 5th root of p to the 3rd. And that is simple as you can write that expression. You pulled out as much from under the radical as possible, or you reduced the fraction as much as possible. All right, so let's try the next problem. Now, it would be best if you pause the video and try this on your own and then check your answer. So I'm going to go ahead and do it. actually I'm not going to do this one. I'm going to remind you if you had this problem, you would simply multiply the 2a times the negative 3a, and that would give you 6a squared, and then you would multiply the x and the y, and that's it. Simple as that. So one mathematician's trick is when you see a lot of clutter, think of a simpler problem that's of the same nature. This is all multiplication. This is all one term. So what I'm going to do is multiply the coefficients together, because multiplication is commutative and associative. I can ignore these parentheses. And I'm going to multiply the radicals together. Now, you could do this in fewer steps than I'm showing, but I want to make sure I show all the details. Okay. Now, the first part's easy. That's just 6a squared, right? Then, again, just ask yourself, do I want to try to simplify two separate radicals, or would I really just rather simplify one? I'd rather just simplify one radical. So we have our rule that says if you are multiplying two radicals, you can make one big happy radical, and multiply under that radical. So that would be 8ab cubed times 6a to the 8th b cubed, all under the same radical. And what makes this easier is you can simplify under the radical. So I'm copying over the 6a squared. 8 times 6 is 48. A times a to the 8th is a to the 9th. And b cubed times b cubed is b to the 6th. When you're multiplying the same base, you add the exponents. All right, so I have to simplify this one radical. It's not so bad. Remember, identify any perfect squares right off the bat. That's helpful. B to the 6th is already perfect. How do I know b to the 6th is a perfect square? Because the exponent's even. I'm not messing with the b to the 6th. The 48, is that a perfect square? Well, this is why there's a list of perfect squares for you to be familiar with. 48's not one of them. So does a perfect square divide into it? The largest perfect square. That's kind of tricky. 4 is a perfect square. That divides into 48. But so does 16. And don't be afraid to use your calculator. Like 48 divided by 16. See if that comes out even. It does. So 16 times 3 is 48. Now, a to the 9th is not a perfect square. I know that because that's not an even exponent. But is there an even number less than 9? Yeah, and you want the biggest one, so that would be 8. So this would be a to the 8th times a to the 1st times b to the 6th. Okay, now, you can split this up, radicals. You can reorder everything if you want to write a lot in paper. I really don't want to. These are my perfect squares. I'm going to take the square root of those. And when I take the square root of them, they come out of the radical. So this is 6a squared times, what's the square root of 16? 4. What's the square root of a to the 8th? Cut the exponent in half. That'll be a to the 4th. What's the square root of b to the 6th? That'll be b cubed. And what's left under the radical is just the 3 and the a. Okay? And now the coefficient to the radical is a mess. Let's clean that up. 6 times 4 is 24. A squared times a to the 4th is a to the 6th because I'm multiplying the same base. I add the exponents. Times b cubed times the square root of 3a. And that's as simple as you can write that term. Okay. Now, the next two problems are of slightly different nature than the one we just did. That kind of throwback review problems. Notice I have a product in parentheses squared. Okay, so this really, notice again, I can do this. Again, I can write a simpler problem. Well, if I had negative 2x squared, that's a product, I would square the negative 2 and I'd square the x, right? Well, that is essentially the problem I have here. I'm going to square this factor, and then I'm going to square the radical, which is the other factor. And then negative 2 squared is 4. But notice the relationship. It's 4 times the answer to this squared. So it's 4 times whatever that entire answer is. And then here we are assuming all variables are positive, and this is definitely positive. Because when you square a number, that's positive. Plus 4, that's positive. So what's the square root of something squared? So remember, if you start with a kitty cat and you take the square root and you square it, you're just back to the kitty cat. Okay? So this would be back to x squared plus 4. And you could leave it that way, or you could distribute the 4. For these problems, it won't matter. We will use this skill for solving equations. And when we use this skill for solving equations, we'll wind up distributing, because that's what we'll need for the next step. We'll need terms for the next step instead of factors. But since we're not going any further with this problem at this time, you can either leave it this way or this way. Okay. Now the next problem. Oh, turn the camera off, turn the video off, excuse me, and give that a shot. Let's see if you make the cardinal sin of algebra students. Okay, so I'm going to go over this. Do we have a rule that says you can split radicals along subtraction? Is this the same as the square root of 4a squared minus the square root of 16a to the 4th? Which then people would say minus 2a minus 4a squared. Did you try that? No way. We saw examples like that, that we put in numbers, it didn't work. You cannot split radicals along terms. That is addition or subtraction. Those are two terms under that radical. But we were splitting radicals up here. You can split radicals along factors. I need factors if I'm going to simplify this. Well, maybe I could factor what's underneath here. And I sure hope one of my factors is a perfect square. So first step in factoring is a GCF. GCF is 4a squared. Open your blank parentheses. 4a squared times what will give you 4a squared back? That's a 1 minus 4a squared times 4a squared. Now that I have a factor, I can split the radical along the factors. That's the square root of 4a squared times the square root of 1 minus 4a squared. Under this radical, that's a perfect square. So I can just take the square root, that's 2a. Under this radical, there are two terms. And I can't factor that anymore. I can't split a radical along two terms, so that is going to stay under the radical as 1 minus 4a squared. And this is as simple as you can write that. So be warned. Yeah, I will definitely be checking to see if you will try to split a radical along terms. I remember teaching a pre-calc class and people doing these really, really, they got the word problem bit and they wound up with something like that, and then they blew it in the end by splitting the radical along terms. Don't go there. Don't do it. Now, here, I'm not going to skip this problem. I'm just going to go over it quickly since I'm on video rather than in class. There really isn't much you can simplify with this problem, but what you're going to see, if you left your answer like that, in the back of the book, you'll see it like this. They're going to pull the negative out from the radical because the cube root of -1 is -1. It's a perfect cube. So I can take the cube root of -1 as -1. And so you will see for odd roots, negatives being pulled out from under the radical. They're just better outside the radical. All right, one last tiny little problem, which might show up on one of your graded assignments or on the test. Do not assume the variables are positive. What does that do to the problem? This seems really simple. What's the trick here? Do not assume the variables are positive. Well, that means when I squared m, if it was negative, I lost that negative. I'll never get that negative back. So the square root of m squared isn't necessarily m. It's the absolute value of m. Okay. And then if that p was negative and I raise it to the 6th power, that's going to be positive. And when I take the square root, I'll never get that negative back. The square root of p to the 6 will be p cubed, but at best, I'll get the absolute value of p cubed. And there's a whole list of rules of what you can do with absolute values. You can also write this as the absolute value of m times p cubed. So once in a blue moon, I'm going to pull back and say, hey, don't assume your variables are positive, and remind you that you're going to need the absolute values.